All right, so course should be unlocked now. I have the syllabus up. Let's just go through that real quick. Then we'll start jumping into other stuff. All right, so this is 535. It's a programming class. So this class assumes you've never programmed before. Unfortunately, it's also an 8-week accelerated course. So that means that you are learning programming in a format that isn't conducive to learning programming. But such is life. So we're going to try to squeeze it into 8 weeks. And kind of here's the issue. I'll just give you a top level thing, and then we'll talk more about it in a little bit. But how many of you play a sport? Soccer, tennis? Hey, what's your sport? Soccer. Are you good? Didn't I talked to you last semester about it? You're good at soccer, right? Yeah. So, but you can't just watch soccer on TV and get good at it, right? You got to practice, lots and lots and lots of practice. Well, programming works like that. So to become a good programmer, even to become an okay programmer, takes a lot of hours of effort to put in. And you have to make a lot of mistakes and then fix your mistakes and all this stuff. And unfortunately, that's not real conducive to doing something in 8 weeks, but that's the format of the class. So, having said that, I guess prepare for the worst. Grades in the class. Scroll down here. Homework assignments are going to be worth 60% of your grade. I also give pop quizzes. Pop quizzes will count as homework assignments. Okay, so that means if we're in the middle of class and I'm asking questions and we're not getting a whole lot of feedback, we're not having fun, people have got their eyes down in their laptops or whatever, pop quiz time. Okay, one of my hobbies is human misery. Okay, when you're sad, when you're suffering, I'm happy. Okay, you understand? This is all recorded. We're fine. So that means have fun, participate in class. We were here for 4 hours once a week, right? And maybe you'll minimize the number of quizzes. Or maybe I'll give you an easy quiz. So you get like easy points, right? All right. So there's going to be 2 exams, a midterm and a final. Midterm will be the second half of class week 4. And final is going to be the final class, week 8. I do have a policy that if you do better on the final than you did on the midterm, I will replace your midterm exam grade with whatever you get in the final. All right. Several of you will not do well in the midterm. Again, because you won't catch on as quickly as maybe other people might just because of the nature of the material. Well, the good news is you have a second chance to fix that with the final exam. Make sense? So even if you get a 0 in the midterm, you can still get an A in the class. And I'm mostly talking to you. I mean, you said you didn't like the hard thing. It's going to be hard. You know what I'm saying? All right. We do have a textbook for the class. It's in the syllabus here. So you go to this link, zybooks.com. There's a code. You have to subscribe to the book. It's like, I don't know, $50 or something like that. It's an online textbook. We're going to be learning Python in here for the programming language. All right, so this book has a whole bunch of interactive stuff in it. So I'll be giving you assignments out of this book as well as regular assignments. So this actually has you do things, fill in the blank here, test stuff. So it's very much an interactive experience. I've used the book several times. It's a good experience. So get that as soon as possible. You'll have it available to you instantly. Okay. That's it for the syllabus. Okay, questions about the logistics of the class, I guess. Makes sense where your grades come from? Blah, blah, blah. All right, so some pet peeves. So first of all, with homework assignments, I'm fine with you guys working in groups or whatever for homework assignments. Okay? I'm not concerned about that. I'll find out on the exams if you're learning stuff. I'll find out on the quizzes if you're learning stuff. All right, so you're going to learn a certain amount of the stuff in class from me, but some of you might not understand everything I say. And maybe it's helpful to work with fellow classmates on the homework assignments, and maybe you'll learn something from fellow classmates, or maybe you'll be able to help teach classmates, right? So I'm not going to be looking at your homework assignments trying to find cheaters. Okay, I don't care. I'm going to find out about it on the quizzes and the exams. So when you work in your homework assignments, I want you to work on them with the intention of learning. Okay, now what does that mean? That means don't just get into a study group and expect somebody else to do all your work for you. At the very least, ask a lot of questions and try to be more of a participant in each homework assignment. Big pet peeve of mine. And if I find out you're doing this, your grade is toast. Don't pay people to do your homework for you. We recognize that that's been an issue in the MSIT program before. In other classes, students will pay other students, even former students, to do your homework. Again, I'll find out about it in the midterm and final when you don't know what you're doing. And keep in mind, that's 40% of your grade. And what do you need? You need a B- in here or better in order for the class to count. Okay? So it wouldn't be in your best interest to blow off 40% of your grade because you don't want to work on your homework. Make sense? All right, but if I find out that anybody's paying somebody to do their homework for you, we're going to have problems. All right, incredibly unethical. Not just from the student's perspective, but also the people that are charging people to do homework for them to do homework. Like I know some former students who offer their services to do homework for existing students. That's terrible. It's something you would do. Well, I'm just getting warmed up. So far, you're the easiest target. Low-hanging fruit is the. All right. So everybody gets that homework is where you'll be learning stuff, and I'm giving you a lot of your percentage of your grade from that homework. There isn't an excuse for anybody not having a high A homework assignment average, right? I'm encouraging you to work in groups. Heck, I don't care if you all get together as a whole class and work on your homework. It doesn't matter to me because I'm going to find out on these two tests whether or not you're learning or whether or not you're mooching off other people's work. Make sense? Okay. So do yourself a favor and, the very least, participate in the learning experience. Okay, I do record all of my classes, so I put the lectures up on YouTube, so there'll be a link on here. I also share the slides, so we'll have an organic slide set that will be growing as the class goes on. This is already linked up there, so if you click on the link right now, you'll see exactly what I'm looking at. So that means, I encourage you to take notes, but you don't have to write down everything that I say, because I'm going to be putting it here on the slides, and you have access to the slides right off the bat. Make sense? Okay. My classes are very interactive. We'll have conversations. We'll be laughing. I'll be making fun of people, mostly him. Okay. But once I start to get to know some of the rest of you, I'll make fun of all of you. Okay. Ways to get away from that is bring me coffee. Okay. So, yeah. Nice sweater, by the way.
Thank you.
Yeah. I do like it. I don't know about the turtlenecky part of it. I'm not a fan, but. It's a gift. You see, I don't get a lot of clothing as gifts. So, I seem petite, but in real life, I'm actually quite large. So all my clothes comes from tent and awning stores. You have those in Nigeria, right?
What?
You have tent and awning stores in Nigeria. You know what tent is, right?
Yeah.
Yeah. So when they have to make big things out of vinyl and burlap.
Right.
Yeah. So that's where I get my clothing. It's like the stuff they're using to cover houses.
I really shouldn't be laughing.
Ha! All right. Yeah, so get the book as soon as possible. I'll be giving you your first reading and interactive thing from the book later on today. Class does go for 4 hours. We will almost always go all the way to 10 p.m. Sometimes we might even go to 11 or 12. Depends how, what kind of behavior we're dealing with over here and here. And a little bit back there. And as I mentioned to another student coming to class, we will take 30-second breaks. You get 2 30-second breaks. It's a stretch, right? No, seconds. Well, you need more than 30 seconds? So the frequency and the length of your breaks is directly proportional to how interactive class gets, because the more we're talking back and forth, the more you're learning, the more I'll be convinced that the stuff is actually getting digested, and the less time we'll actually have to stay together in the classroom. Make sense? Okay, so the only person I really want to shut up is him. Everybody else should talk a lot. Well, no, I'm definitely pointing at. All right, questions about anything with the class at this point? Can we just dive in? Ready to go? All right, how many of you in here have ever done any computer programming? Remember, I'm assuming nobody's done any programming, so your answer will not hurt you. All right, so you've done something? What have you done?
C# and Java.
C# or Java, how much?
2 years.
2 years. Okay, so when you get stuff wrong, you'll be the one who's embarrassing themselves because you've done this a bunch. So my goal now is to trick you.
Oh, no.
Okay, because I actually just started programming last week, so I'm a week ahead of you guys.
That's not true.
How do you know?
I've heard about your legend.
I just started this stuff. All right, so what is programming? When you think of computer programming, what do you think? What's the first thing that comes to mind? Code. Okay. What else?
Instructions.
Okay, so that's kind of a more formal way of saying code. Something like a tea drinker would spit out type thing. Why do we program? What are we trying to accomplish?
Solve a problem.
Okay, what kind of problem?
Depends on the problem, what you're looking at.
Well, would we write a program to shovel snow?
Yeah, for that we need to make a hardware.
So when we're writing programs, we're trying to tell some hardware what to do.
Yeah.
Right? All right, so what's computer programming? It's telling a computer what to do. Simple as that. We don't have to go any deeper than that. I mean, that's our goal. As technology professionals, we want this guy to do our bidding, right? To bend to our will so that we can go be lazy and watch one of those reality shows or something like that, or some of the stupid shows like was it World Cup Soccer? Is that the Premier League? What's the Who's a cricket fan in here? A cricket fan? Like cricket? Several years ago, some of my students tried to get me to watch it was the Cricket World Championships. I think it was India versus Sri Lanka. I think Sri Lanka won, if I remember correctly. And so I'm watching it. I don't really understand this sport. And it went on forever, like hours and hours and hours. And then in the end, this team was cheering. Now, one would think that the team was cheering that they won. They didn't. That was the losing team. They were happy it was over. Like, oh, finally, the game has ended. Yeah, so it must have been the Indian team that was cheering. Yeah, I didn't understand that thing. It was a made-up sport. You should look at real sports like golf. All right, so what's programming? We want to tell computers what to do. Okay? Now, why is that hard? I've sat up here at the beginning and told you that computer programming is hard. Do you believe me? We got 2 years of experience here, so I'm the guy with only 1 week. So I mean, I don't really know what's going on here, but you find computer programming hard?
Yes.
Yeah, it's a tough thing, right? Now, all of you have a lot of experience dealing with people, right? We deal with people all the time, but not so much experience dealing with computers. Now, even if you're a computer user, you're good at Microsoft Word, or you're really efficient at finding things on Google, whatever it is, you don't necessarily think like these guys do, because these guys don't think, right? So, call this the problem. Now, you mentioned something about solving problems. Now, specifically, we're trying to solve problems. Well, we're trying to tell this guy how to solve problems for us so that we don't have to do it ourselves. So typically, we want him to solve problems that he's going to be better at solving than we would be ourselves. But we still need to be able to tell him the steps that need to be taken to solve the problem. So what's the real problem with becoming a good programmer? It's that humans are so good at solving problems that, So let me pause here for a second and ask the question. How many of you got to class today without bumping into any walls? You're walking down the hall out here? Any of you bump into any of the walls? Fall over? Nothing? Nothing. You got here, no problem. How many were texting while you were walking down the hall? At least a couple of you, but you've seen people text. You know, you're walking down the hall and their eyes are just buried in their phone, right? So nobody in here bumped into any walls. You were carrying hot tea. I assume it's hot, right? Yeah. How did you do that? How did you get from the parking lot to this classroom without falling over, without bumping into any walls, all that stuff? How did you accomplish that? You just did, right? It wasn't even worth your time to pay attention. Could you have texted on your phone and carried the tea at the same time while you were walking to class? Yeah, no problem. You probably still would have missed bumping into any of the walls, right? Because walking is easy, isn't it? So tell me, how do you walk? If you were to give me instructions on how to walk, what would you say?
Lift your left leg.
Okay, what's a leg?
It's part of the body.
Part of my body. Oh, what's a body? Is it this thing? Okay, so I got to lift my left leg. So here, I'll give you a starting point. I know the body, I know the leg. So I got to lift my left leg.
Yeah.
Right here, I should stand for this, right?
Yeah.
If I go down, this is, okay, it's lifted. What do I do with this?
And then plant it forward.
Do who, what?
Plant it forward.
Plant it?
No, like you put it down forward.
Put it down. Okay, how do I do that?
Step forward.
Step? What's a step?
Move forward.
Move?
Move forward.
All right, you have to tell me how I'm going to have to do that. How do I move forward? Is it like a... How many muscles do you use when you walk? Like a bunch? A whole bunch of muscles, right? Now, when you're walking down the hall, are you thinking in all this detail, like, okay, I need to, extend this muscle or contract this other muscle? You're doing all those details inside your head, right? You're just thinking about every little twitch. No, you just do it. How? You've been doing it for so long, and you're so good at it that you've forgotten the details of how to do it, right? So when you were a baby, at some point you picked yourself up off the floor and you fell over. And you picked yourself up again, and you kept doing it over and over and over again until you stopped falling. Then you started moving and falling. And then you started moving and not falling. To the point where we are today, where you can walk around no problem. The problem with becoming a good programmer, or even an adequate programmer, is that as human beings, we are so good at solving problems that we find it difficult to articulate how we solve them. We have a lot of trouble explaining to other people how to solve problems that we take for granted. So let's take a software application, whether it's a video game or an operating system, some complex piece of software. So let's just randomly say the latest, greatest video game with all the explosions and all that stuff. You think that's probably pretty hard to write? I think that's a really difficult computer program to program, to write the software for? Okay, well beyond us, right? Okay, which do you think is harder, learning to walk or writing that software? You think writing the software is harder. Learning to walk is not just harder, It's orders of magnitude harder than writing that software. That software is an example of the best that we can do. That's the hardest kind of problem that we can solve, where we are still able to articulate the solution to the problem. If we can't explain how we're going to solve the problem, we can't write the code to solve it. Well, we've already proven here that we can't explain to somebody else how to walk, right? We can't break it down into the little tiny steps. Do you suspect no matter how long we tried, we could probably sit here for a week and not get every little step? People would still be falling over. So the way you teach somebody to walk is through practice. Get up, fall down, get up, fall down, just let them figure it out. So it's not even your instructions. They're just figuring it out themselves and whatever that means to them. We have to be able to fully articulate the steps to solve a problem in order to write software to do it. That's why most of the software we write today, even though we might perceive it's really complex, is actually very simple compared to the types of problems that human beings solve on a daily basis. We are really, really, really good at solving problems. We're so good at solving them that we can't tell other people how we do it. We're too busy texting while we're solving them. That make sense? That's the problem. So, what's the solution? Well, first of all, I want to think about, how do humans solve problems? I like to break this down into 3 steps. Okay, we ask questions. I'm sorry, let's start with this. Let's say memory, ask questions, and repetition. All right, let's start with the first part of this. How many of you know your own name? All of us, right? Hopefully everybody in here, if we went through and took attendance, everybody, if when I called your name out loud, you would know that was you, right? Even you. And I have real low expectations. All right, so how do you know your name? Is it stored in here somewhere? And even though you're not necessarily aware of it, if somebody asks you what your name is, you kind of believe that you're somehow kind of looking it up real quick, right? You're like, oh, my name's Mike. So you're looking it up real quick and you spit it out. You're retrieving that information. Now you kind of have like your conscious memory, and then you have like long-term memory. So you got some of those old stories and stuff that you kind of have to think about for a little bit to kind of recall. You know, it's in cold storage, right? Old memories are probably, I'm guessing, from drunk nights. And no, we're still right over here with you. Is that your partner in crime? So, you know, we have that kind of old storage, it's a little bit slower, and then we have kind of our fresh storage, right? Somebody asks you what your name is, it's right there. Phone number, right there. Address, right there. Things like that, right? You know, what did you have for lunch? Probably right there, depending on the amount of alcohol. Right, Judy?
Huh?
Him? He's a bad influence, isn't he?
He's a good guy.
I'm gonna change seats.
you just think I target whatever's there? Yeah, see, that's the thing, is my chair only turns so far. See that? So, right. So memory is pretty important. If we didn't, you know, movies make fun of this, right? Movies make fun of people who get like short-term memory loss. You know, somebody walks in and says, you know, hey, I'm Mike, and then like 2 seconds later they forget they ever met them. Like, hey, I'm Mike again, and it's funny for a second, but think about how debilitating it would be if you didn't have memory. Okay, so the way human beings solve problems, one of our main tools is by remembering things. Okay, now we ask a lot of questions too, don't we? So as you were walking down the hall, not bumping into the walls, even though you weren't necessarily aware of it, do you think that you were probably going through kind of a checklist of questions like, am I going to hit anything? Do I need to turn left? Do I need to turn right? Am I falling over? Do you think you're constantly kind of asking those questions? even though it's kind of like in the back of your brain, you're not really aware that you're doing it. You're making little tiny adjustments, right? You know, if you're kind of swaying to the left, maybe you shift your weight a little bit, that kind of stuff. All right, so we ask a lot of questions when we're solving problems. And repetition. So human beings, we like to repeat things. We like steps. So walking, we kind of have an algorithm, a set of instructions for walking, and then we repeat those set of instructions over and over and over again to ultimately produce that movement. Okay? So now, what's a CPU? Central Processing Unit. That's what it stands for. What is it? Brain of a computer. Okay. What does that mean? Let's really get down to the nitty-gritty of what a CPU is. Because you know what's funny? Is most technology students have no idea how a CPU works. They just know it's the brain. They know what it stands for. What does a CPU ultimately do? Okay, so now, okay, so you said binaries, like bits, zeros and ones? Okay, so you think the CPU works with zeros and ones. All right, so that's kind of the language he speaks. Okay. When you say he works with it, what does he do?
I mean, at the end of the day, everything kind of boils down to zeros and ones. That's how it processes information at the end of the day.
Okay, so when you say processes information, what do you mean by that?
So, for example, as you're typing, as you're the brain of a computer, every single word was represented as zeros and ones. That's what the CPU actually understands. Okay,
so the CPU understands zeros and ones. Yes. Just randomly, I just throw zeros and ones at it.
That's
what you got?
I think it helps a computer to think.
It helps a computer to think. Okay, how does it do that?
Like, if you input anything in the computer, it will process it and try to produce it.
What?
It will.
Is it safe to say that we probably have kind of this generic-y idea that a CPU is really important? It's a part of the core movements of a computer, right? You know, if we're going to draw a picture of a computer, you know, we might come in here, we might say, okay, well, here's our CPU, and then, you know, what other parts do we have? We have you mentioned memory. So we have a RAM. We'll squeeze that down a little bit. Put it up here. All right, and then you mentioned, oh well, you didn't necessarily mention it, but we have a hard drive. Hard drive or solid state drive, something like that. Then what we kind of have I/O stuff. You mentioned something about keyboards and crap, typing stuff.
Yeah.
All right, so I/O devices. All right, and the CPU is just part of that whole system, right? And then kind of in the middle, all these guys have to talk with each other somehow, right? How do they talk with each other? Bus. We'll make that yellow. It's pretty. All right, so there's the bus. So the bus is the communication channel, and there's multiple buses that all these things are speaking with each other through, okay? Now, the CPU is just one part of this. Now, you've mentioned that this guy speaks zeros and ones, binary, okay? Then you babbled on about something. What were you saying?
I was trying to explain that it is the brain of computer.
Where I got that. We got the brain of the computer.
Execute command that's taken from the user.
Okay, now we're getting somewhere. So you're saying this guy executes commands? What commands does it know how to do? Yeah, where do the commands come from?
From the use of computer.
Oh, so we could just tell a computer anything. So I could stare at this thing and say, okay, I want you to wave at me.
No, you have to use hardware to reach your commands to the CPU.
Okay, so I like to think of it like this. I think a CPU is a collection of magic tricks. We're going to talk about that here in the next couple of minutes. Okay, but first of all, we're going to do a test. Okay, so everybody put your arm up. Everybody's got to get your arm up. All right, so now just put one finger in the air. Everybody was able to do that? Okay, now, open hand again. All right, now make a fist. All right, so we just introduced two magic tricks that we know how to do, right? We know how to put a finger up, and we know how to make a fist. Now, can we wave our arms back and forth like this? All right, so we're starting to see all these little things that we can do as individuals, right? Now, is anything that we just did impressive? Or is it all like little stupid movements? Right? Is it important that we're able to move our finger? Is it important that we're able to move our thumb? Are those important things? Are you impressed that I can do that? Nobody's going to give me $5 because I can do that. But you're saying it's important. Why is it important?
You will use it in your daily life.
How?
When you want something, you try to open the car door, something like that.
Okay, so when I'm going through daily life and I'm solving problems, like we already decided, human beings solve problems constantly, right? We're really, really good at it. All these little tiny movements that are meaningless in the big scheme of things, right? Nobody's impressed if I can do this. Nobody's impressed if I do that. Nobody's impressed if I do this. But when you start putting all those things together, you can solve real problems. Does that make sense? So as a human, we're kind of like a CPU. Well, really, a CPU is kind of like us, where there's a collection of things that a CPU knows how to do. And those individual things may not be impressive in and of themselves. But if you link several of those little things together in a certain order, something real happens. A problem is solved. Make sense? Okay. So a CPU is a collection of magic tricks, where a magic trick is those instructions. So from our example, that's a magic trick. That's a magic trick. That's a magic trick. I don't know when we're going to use this. I guess hailing a cab. Okay. And then if they pass us up, we have another gesture that we might use. I learned it from him. All right, so that's what a CPU is at the high level. So now we go back here to when we were talking about what is programming. This is telling a computer what to do. At the end of the day, aren't we really? We're telling the CPU what to do. Now, what does it mean then to tell a CPU what to do? We have to tell that CPU how to solve the problem that we want it to solve in terms of the magic tricks that it knows about. You mentioned that I might need to do the thumb thing and stuff when I open a car door, right? So if you were to explain to me how I open up a car or how I pick up this soda, you might say, okay, first, extend your arm. Then, I guess we can maybe do one finger at a time. Magic trick 1, magic trick 2, magic trick 3, magic trick 4. Then 5 is clap, or clasp it together. Then lift, bring towards mouth, drink, something like that. A whole bunch of little tiny steps led to me being able to pick up the soda and take a drink. But we needed to, it wouldn't have worked if I did those out of order. I can't do that and then I punch it, knock it over, or something like that. So the order was important. So when we're talking to our CPU, we have to explain things in those little tiny steps as well. Now, even if we go back to older processors, like an Intel x86 processor, which has far less instructions, far less magic tricks that it knows than our modern processor today, there was still a bunch of things it knew how to do, right? So whenever we tell a computer how to solve a problem, we have to tell it in terms of the things it knows how to do. That make sense? All right, so you mentioned a couple minutes ago something about zeros and ones. So let's talk about that thing. So you talked about digital stuff, right? So digital stuff is zeros or ones, on or off, that kind of stuff, right? Why? Why zeros or ones? Why is that what a computer, why do computers like those? Because they who, what? Why? Did the person who built the computer just say, buddy, this is the one? Why didn't they do Spanish? Or French? Ah, it's the nature of electronics, right? So we got electricity. There's electricity involved here. And sometimes things happen when electricity is flowing. And when we don't want those things to happen, we need to make sure the electricity doesn't flow. So we turn it on and off, zeros and ones, zeros and ones. So at the end of the day, it makes a lot of sense for a computer to operate off of zeros and ones. Okay. Now, how many of you are looking to get a job when you graduate with your master's degree and you want to go out and work and make some money, right? Most of you want to go work, right? How many of you want to stay in the United States to work versus go back home? Several of you want to stay in the U.S.? All right. How many of you want to do the job where you go to work every day and they give you the little 2-button keyboard? Just have 2 buttons. You have a 0 and a 1 key. Just all day long, you're just tapping it out. 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1. How long until you go insane?
1 minute.
Yeah. How long do you make your first mistake? 10 seconds in, something like that? That's not what human beings are qualified for. Okay? That would be very, very difficult for us. This guy loves that. So a little bit ago, I mentioned that human beings are really, really, really good at dealing with other human beings. So we do it all the time. You know, even in this room, we have some language barriers, right? Okay? But we still can communicate with each other. You're reading facial expressions. You're reading the way I might say something. You can tell when I'm joking versus when I'm being dead serious that I don't like you. I do like you. Just have a big smile, so I figure you roll with the punches pretty good. You know, he's usually pretty easygoing, but he's got the tea thing going on right now. It's a little bit. So, now, how many of you in here speak more than one language? Several of you, right? Now, when you're, you were Saudi, right? Okay, so when you're back home or even here speaking to your buddies in Arabic, isn't the same thought process going through your head as when you're speaking to somebody in English? Because you're talking to humans. And I realize you got some differences in language, and sometimes you have to kind of think about where the adjectives go and stuff like that. But in general, because you're talking to a person, your thought process is the same. The words that are spitting out of your mouth might sound different, but it's the same thought process because it's a person. And we're good at that. Right? When you're first learning English and trying to talk to people over here that all say you have broken English and crap like that, most of the problem is that you think we're speaking too quickly, or phrases that you're translating from your language into a phrase here that just doesn't sound quite right to us. Those are piddly little things, right? Most human beings can kind of figure it out in the middle. Like, oh, that's what you meant, right? And after you get to know somebody, and then you don't have any problem talking with them, because we're all humans and we kind of figure out how we think, how we communicate with each other. But now we got this alien sitting here that understands zeros and ones. Now, I don't care how much we practice, we're not going to be able to talk to this guy with any sort of efficiency in zeros and ones. That's not our cup of tea, pun intended. All right, you get it? That's not for us. So we need something. We need an interpreter in the middle. We need a tool that's going to allow us to talk to this guy, because at the end of the day, he's talking zeros and ones, right? And at the end of the day, we're not. It's not for us. So what's a programming language? We've talked about natural languages a little bit, like English and Arabic. These are natural languages that are built for a human being to talk to another human being, right? Now, how perfect does a natural language need to be? Or are human beings pretty good at kind of filling in the gaps? See, we're almost spoiled with how good people are at solving problems. You can say something in the worst possible way. You might not even know what you're talking about. Like, I don't know if it's 3, 4, 5 streets down, just make a left. There's going to be this hair salon on the left side. And people will figure out where to go. Because human beings can solve problems and they can figure out, they can fill in the gaps. They can fix your mistakes, right? As long as you get them in the right neighborhood, they're probably going to find their way to your house for the party. Okay, I didn't get my invite, by the way. Yeah, next time. All right, I'm going to hold you to that. So, those are the languages we're used to working with. We don't have to think at that level of precision that we have to when we talk to a computer. Because when we're talking to a person, we're going to assume the person will just figure out what we meant, which might not necessarily be the same thing that we said, right? So if a natural language is a tool that allows a human being to talk to another human being, a programming language is a tool that allows a human to talk to a computer. Okay, fine. It may be easier said than done, because we've already decided that this guy's like an alien. He's expecting zeros and ones, and we're not going to do that. Okay, so that programming language better be a pretty powerful tool, right? Now, how many of you are willing to meet the computer halfway? Computer speaks zeros and ones. We speak the polar opposite of zeros and ones. You know, so zeros and ones, very discrete, very exact, on or off. We're humans. We're all sorts of shades of gray, right? We speak with all sorts of ambiguities. You know, very little detail. Lots and lots and lots of room for interpretation when a human being is talking. All right? So if I'm sitting here, this computer's in the middle of Lake Michigan somewhere in terms of how far apart we are between natural languages and zeros and ones. How many of you are willing to meet this computer in the middle? Figure out something that gets us halfway. Whatever half of speaking zeros and ones is compared to a natural language. No! We're humans. We're higher up on the food chain. Why should I have to drop down to this guy's level? He's lucky I'm wanting to talk to him at all. Right? I expect more from my programming language. Okay? I'm willing to drop a little bit. Okay? Like 5%, right? I'll drop 5%. So as long as I'm about 95% of the way of how I'm already used to doing things, I'll go there. So we're expecting quite a bit out of our programming languages, right? Okay. So there are 3 kinds of programming languages. As we already mentioned, we have machine language. We have a low-level language. And we have a high-level language. Now, low-level languages are zeros and ones. Or I'm sorry, machine languages are zeros and ones. And we've already discussed that's not really our cup of tea. A low-level language has a one-to-one relationship. Butchered that. Relationship with the CPU. What does that mean? What does it mean to have a one-to-one relationship with the CPU? Well, earlier we mentioned that the CPU is kind of a collection of magic tricks, right? So it knows how to do, maybe let's just say it's 100 different magic tricks, little tiny things that when you do enough of them in a row, maybe something real gets solved. Well, a low-level language allows us to not necessarily speak in zeros and ones to the CPU, but we're still giving individual instructions. So if you were speaking to me in a low-level language and you were teaching me how to pick up my Mountain Dew to take a sip, you would say, extend your arm, close your index finger, close your middle finger, close your ring finger, close your pinky, apply pressure with your thumb, lift the can, retract your arm, individual little steps. Is that very natural for us? It's doable. That's way better than zeros and ones, right? But not real natural for us. If a human was just saying, like, oh, I want to take a sip of that soda, it's like, okay, well, grab it and take a sip. That's what we'd say, right? If somebody can't figure out how to grab it, they don't deserve the soda, is what it comes down to. All right. Now, just to give you an idea here. So hook it up. How many of you have heard of assembly language? Have you heard that phrase before? So a low-level language, an example of a low-level language is assembly language. All right, so that's a one-to-one relationship language. Now, typically when you first learn to program, the very first program you write is hello world, right? It's just printing something to the screen, okay? So what we're going to do here is we're going to look at an example of hello world in a low-level language, okay, in assembly language. Now, this is written specifically for the Linux operating system. How many of you have ever used Linux or Unix? You use Unix? Most of us are Windows, Macintosh people, right? How come? Why don't all of you use Linux? How many of you have heard of Linux? All heard of it?
Yeah.
Okay. Why don't you use it? Why isn't that your go-to operating system? You used to using Windows? Okay. So what have you heard about Linux? What's your perception of Linux if you haven't used it? Is it an easy-to-use operating system? Not necessarily user-friendly, right? What's an operating system for starters? When we think about operating systems, what's the purpose of an operating system? It's the who? The spirit? Computer? I've never heard that, but I don't dislike it. I'm not sure how accurate it is, but I don't dislike it. I kind of like
The soul.
the salt?
So
The soul of the computer.
CPU, you say that's brain of the computer. This one is soul.
Yeah. Oh, now the thing is, I like the idea, but I'm not sure it's a good analogy. I want it to be a good analogy, but I'm not sure it is. So if we kind of go back, so we had this picture earlier, right, with our RAM and the buses and the CPU and the I/O and the hard drive, all these things, right? Okay. Now when we want something to happen, do we kind of just reach down and start poking? Do we poke at the CPU? No touchy, right?
Yeah.
Okay, why? Well, usually there's a fan sitting on top of the CPU spinning really fast, so you might hurt your fingy, right? Right? So he's all chill with the T thing going on here. So no, I'll touch it. Okay, so that's not how we interface with computers. We need something that will talk to that hardware for us. All right, because we're not going to be sitting there with little soldering irons and stuff like that, and it's like, oh, I'm going to touch this wire. Oops. Okay, that's not how we work. If you look back at those computers from a long time ago, the ones that, how many of you have ever heard of UNIVAC or EDVAC? Here, let's here, I'll bring up a picture. Let's look at UNIVAC. Yeah, look at this guy. Yeah, that was a computer. It took up like gymnasiums. And this computer is like, they had the power like one of our calculators. You know, barely could do anything. And it used something called a vacuum tube. Okay? Which kind of think of that like a light bulb. A light bulb. So if you wanted to represent some numbers, you turn some light bulbs on, turn some other light bulbs off. Right? So you would go up and actually manually turn light bulbs. So that might have been kind of fun to use that computer for like a day, just to say you did. But wouldn't that get pretty tedious pretty quick? If you wanted to add the number 5 to 7, to have to go up and screw with a whole bunch of light bulbs to do that? Plus, you have to walk halfway across the gym because those light bulbs aren't even right next to each other. They're all over the place. This little tiny computer that barely does anything is taking up the whole freaking school. What happened? How do computers get this small? How did we go from twisting light bulbs, twisting vacuum tubes to this or to this? What was the big invention in between there? Silicon?
No.
It's a problem. Students are too young today. They don't remember the wars. Who? Did you say transistors? Yeah, that's what you should have said. Yeah, so it was a transistor. Okay, so what does a transistor do? A transistor is effectively a switch. So it replaced that vacuum tube. It was also a lot smaller. So now our CPUs today might have billions of transistors on them. So the more transistors, the more stuff we can do, right? And they take up a lot less space. Transistors are tiny. And our computers keep getting smaller and smaller and smaller because our engineering allows us to put more and more transistors in the same space. And now we're sitting at the point where our enemy is like heat. Our enemy is also, when you get two transistors so close to each other, I mean, we're talking like at the atomic level, or not quite atomic, but close to that, like microns. We can only get them so close before they start interfering with each other. That's what's really driving, we're kind of running out of we're hitting some of the limitations of silicon. How closely we can get wires together before they start interfering with each other. But unimportant for us here. But the issue here is when we went to transistors and computers started getting smaller like this, and they started putting covers on them and not letting us twist the light bulbs, all of a sudden now we need an operating system. We need a piece of software that lives between us and those transistors because we can't just reach out and flip the switch. Does that make sense? So that's what that operating system's for. So this guy sits between the human and the hardware to allow us to control our computers. Make sense? Okay. Now, having said that, the reason I wanted to introduce that is because I think pretty often we take for granted what an operating system does for us. So one example here is that most of you would say that Windows is an operating system, correct? And you would say that Mac OS is an operating system. That's actually not quite accurate. Windows and the Mac OS are what are known as distributions. Just like Ubuntu is a distribution of Linux. Red Hat is a distribution of Linux. The core operating system is the Linux kernel. For Windows, the core operating system is the NT kernel. Okay, make sense? And actually, Mac OS is based on OpenBSD Unix. So it's actually a Unix operating system. Yeah, that's not because Apple's so smart. It's because Apple stole it from the right people. We'll get to that. I have all sorts of good stories of those things. We having fun yet? Is this somewhat entertaining? A little bit? Are you lying to me? We're just in a state of intimidation at this point. Or is the tea gone?
No.
Really, nurse? Did you put honey in it?
No, I'm allergic to honey.
You're allergic to honey? Why didn't you put honey in it? What happens? What happens when you? Are these like really bad?
Yeah, like my throat really starts to itch.
Oh, just itch?
Yeah, it itches like really bad.
Oh, so like not like airway closing, just like you're uncomfortable.
Very uncomfortable. Yeah, it's like the dumbest allergy.
But I just want to clarify, you won't die from it. You're just really uncomfortable.
Yeah, just very uncomfortable.
All right. Now, is it only eating it, or even if it gets on you?
No, like actually, like eating like.
Oh, so if you touched honey, it wouldn't.
No.
You'd be fine. Just want to make sure I get all the information. Who is this person? How horrible! All right. So, anyways, those are called distributions. But the point is, it's fine to say that Windows is an operating system. That's not a horribly inaccurate thing. But the punchline is I think we take for granted what operating systems do for us, because they do a lot. And we're going to see that by example here in a second. How many of you have heard of something called an API? At least seen those letters next to each other at some point? Okay. So sometimes it could be an application programming interface or an abstract programming interface. Those are kind of used interchangeably. It's kind of unimportant what it exactly stands for. What's more important is kind of what it is. So an API is a collection of functions that allow one system to talk to another. Fair enough? Okay, so.
One system to talk to another system.
Yep.
And we use it between system and people.
Well, so an example of an API is, I think the answer is yes, but an API is guaranteed to work. So if I told you to stand up, I'm delivering, let's say that you've agreed that if these 5 commands are given to me, you'll act them out. So if I say stand up, you stand up. If I say sit down, you sit down. That's you responding to an API call. I'm asking you to do something externally. Make sense? Okay. Now, typically, we think of APIs in the software world. Where you might be writing a piece of software that has to interface with like PayPal, something like that. And you want PayPal to be able to do, charge this email address $10. So you might call upon that API, giving it the correct credentials and say, charge this email address this amount of money. And then the PayPal system goes and does that for you, which then allows you to integrate kind of PayPal features into your application. Kind of make sense at that high level? All right, but generically speaking, an API is a way for it's a collection of things that allow one thing to talk to another thing, either retrieve information or send information or ask it to do something, whatever. With that in mind, all operating systems have APIs. All right, so has an API that allows programmers to perform I'll just put it in quotes here, common tasks without having to write all of the detailed instructions to do those things. Okay, so for example, earlier you mentioned something about when you type in some keys and some stuff spits out on the screen. There's a program somewhere that does that, right? Now, is it pretty common across your operating system that very often when you tap on keys, stuff shows up on the screen? Like, we would call that a common thing that happens in operating systems, right? All right, so for example, and this is the exact example we're going to look at here in a few minutes, is there's a system call, there's an API call for Linux called syswrite. And that dude knows how to write something to the screen. Okay? Now, it might be 200 lines of code. It might be 500 lines of code. It might be 1,000 lines of code. Punchline is, it's not our problem. Somebody's written it because it's really, really, really handy to be able to write something to the screen. So that when we write a program, even if we're writing one of those low-level language programs where we're using that one-to-one relationship with the CPU, we don't have to actually write that 1,000 lines of code to get something to show up on the screen. We can do all the logic except that and just tell the operating system to do that part for us. That make sense? So even using a low-level language, if we're using it in conjunction with an operating system, still a lot of work is being done for us. That operating system is a power tool. Okay? And you're going to see this by example here in a second. And then we'll probably take a break here in a few minutes. Let's get that one of those 30-second stretchers. So far, we've been pretty good. Pretty interactive, right? Maybe not quite the level I want it to, but it's kind of the T thing, I think. It's like, you're usually so energetic. This is more like a depressed. You under the weather, got the flu thing going on?
Yeah, I'm recovering.
You're recovering from the flu?
Well, it's still a little cold.
Oh, man, that flu is killer these days. My wife, there's this stuff, it's like a supplement called, it's black elderberry is the name of this. The stuff is called Sambucal or something like that. It's like a supplement that you take to help prevent the flu.
Oh, okay.
And she was turned on to it by my sister-in-law years ago and kind of takes it regularly just as a preventative type thing. Well, now with the flu season here, the word's out. Every place is sold out of this stuff. I mean, it's like stupid. And I mean, I went to 6 different pharmacies today. Nobody has them. I mean, I'm saying everyone saw. I mean, this thing is like, iPhone day one type stuff. It's ridiculous. All right. So let's go and look at Hello World in a low-level language. Okay? So this is specifically for the Linux operating system, so it's going to be using Linux system calls, but it would be very similar for Windows or for the Mac OS. It would just be, instead of syswrite, it might be called display or something like that. A little bit different name for the system call. All right, so this is the actual program right here. All right, so down here at the bottom, we have our data section. So data section, we have a couple of variables. Remember we mentioned earlier about memory? We got to remember stuff. So we're going to remember a couple of things here. We're going to have something called message, and this guy is going to be hello world. So that's the thing that we're going to be printing out to the screen, hopefully. The other thing we're going to remember is something called len, for like length. And this guy is going to be equal to the length of message, number of characters in a message. Right? Don't worry about why. Just we're remembering 2 pieces of information. What we're going to print and how long it is, because syswrite needs that information. Okay? So that's all the data we're going to remember. So now up here, here's the start of our program. Now, in our computers, we have these things, in our CPUs, we have these things called hardware registers. So when we actually think about a CPU, if I come back here, just add a slide in right here. We have our CPU there. There's more than just those 4, but that'll help us for this this example. And here we'll make these guys a different color. So these guys are little tiny memory locations. Think of them almost like USB sticks. Okay, so this is the 16-bit register, this is a 16-bit register, this is a 16-bit register, this is a 16-bit register. Really, 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 really fast memory. That's not very big, and it's very expensive per bit, but it lives right on the CPU. So the CPU uses this for remembering things. Okay, so this is the hardware side of it. So for this example, we need those 4 little buckets, even though there are more registers than that on CPUs. We're not going to talk about those in here, but we're showing the example of a low-level language. Okay, so think of it as like the CPU has 4 little USB sticks that can store a little bit of information on each one. Okay. So this is an instruction, this is an instruction, this is an instruction. So this is one magic trick. Here's another magic trick. Here's another magic trick, so on and so forth, because this is a low-level language. It has a one-to-one relationship with the CPU. Make sense? So what's the very first thing I'm going to do? I'm going to move into this memory bucket, the length, the value of length, which is the number of characters in Hello World. Then I'm going to move into this memory location, the message itself, Hello World. Then I'm going to move into this memory location, the number 1. Well, why the number 1? Because it just so happens that in Linux, the number 1 represents the standard output file descriptor. Operating systems typically come with 3 different file descriptors as defaults. Standard out, standard error, and standard input. Standard input typically is the keyboard. Standard output is typically the monitor. Standard error is also the monitor. Why do you think they have 2, standard output and standard error? Standard error is typically where error messages get written out to. So why do you think there's 2 separate output streams that both go to the monitor? Why is that handy? Think about this from an operating system perspective. The Jeopardy music playing? What's a log file? What do we typically keep inside of log files? Error messages? Stuff like error messages. So might it be handy to log all the error messages in the operating system? So wouldn't it be handy to have a different channel that the error messages come across versus the normal output so that we can redirect those error messages to a file instead of always having to go to the screen? Make sense? So by splitting it into 2 separate things, we can say errors go down this pipe. Normal output goes down this pipe. By default, they both go to the monitor. But if I want to, I can redirect this pipe to go over to this file, leaving our normal output still going over here, but now I'm capturing the errors so that somebody can go back and peruse it later. Maybe a network admin or something like that. Make sense? So just kind of common sense how operating systems might be built. Probably the very first operating system didn't do that. And then all of a sudden they decided, you know what, it would be really handy if these things were separated. So they did. They made them separated in future operating systems. Okay, so it just so happens that the number 1 in Linux happens to be associated with the very first output stream, which is standard output. We don't know why at this point, just I've moved this piece of information into this storage location, I've moved this piece of information into this storage location, and I've moved this piece of information into this storage location. And then I'm moving the number 4 into this storage location. Just randomly the number 4. Why 4? Well, earlier we talked about that we have these things called APIs, and operating systems have APIs. Okay, a set of functions that allow us to tell the operating system to carry out some tasks for us. And it just so happens that in Linux, the function number 4 happens to be associated with the syswrite system call. And that guy knows how to write something to the screen, knows how to write a string to the screen. Okay? Now, I promise you, syswrite is a scary looking program. What's good for us is we don't have to write it. is we're using it. We're calling upon it. We are leveraging that operating system to do a lot of stuff for us. So even though this is a one-to-one relationship language, this is still a power tool because we're leveraging the operating system to do stuff for us. We typically don't appreciate our operating systems because it's just the guy who plays Facebook for us or lets us send our email. But it's doing a whole bunch of stuff under the hood. All right? But at this point, all I've done is I've moved the number 4 into this storage location. So I've performed 4 magic tricks. I've basically played hide and seek without the seeking at this point. So I hid something over here, I hid something over here, I hid something over here, and I hid something over here. Put these 4 things into these storage locations. Then I'm going to interrupt the CPU. And this 0x80, that's the location of the Linux kernel. So this says, I've done my setup. Now, Linux kernel, you do your part. So the CPU pauses, the Linux kernel, the operating system, takes over, and the very first thing it does is it goes and looks in that memory location, EAX, and it finds the number 4 in there. And it goes up and looks up and says, okay, well, what's number 4? What's that function? Ah, it's syswrite. Just so happens that the operating system knows that syswrite requires 3 pieces of information in order for it to work. It needs to know what I'm writing, how long it is, and where am I writing it to. Those 3 pieces of information. It happens to know that how long it is stored in EDX. So it was very important that we put that piece of information inside of that bucket and not inside of this bucket. Okay, so it expects to find the length in here. It expects to find the message in here. And then it expects to find where we are writing it inside of EBX. Make sense? So it goes and grabs those 3 things and then does its thing. Poof, hello world's on the screen. Because of the magic of syswrite. Then our program gets back onto the CPU. What do? We move into EAX, which currently holds the number 4. We move in there the number 1. The number 1, so are we starting to see a pattern here that EAX holds the system calls that we want the kernel to call? So now we overwrite the 4 with a 1. Now the 1 happens to represent the system call called sysexit. And sysexit is the Linux kernel call that ends the current application. Then we interrupt the program again, tell the kernel to take over. The kernel immediately goes and looks in EAX and says, what do you want me to do? It says, well, I want you to do system call number 1. Okay, well, let me go look at what that is. Well, that's system exit. It just so happens that system exit doesn't require any additional inputs. These 3 pieces of information are still sitting in those hardware registers. We just don't need them. So what's the kernel going to do? It's going to end the program. And we're going to get hello world spit out to the screen. That makes sense? Now, even though we've advertised that this guy did a lot of heavy lifting for us, syswrite was a pretty important system call. The Linux kernel did us a solid and took over and did a lot of the work to get those words actually on the screen. Wouldn't you still say that all the other stuff we did was pretty tedious? Absolutely. And at the end of the day, what did this program do? It put the word hello world on the screen. It did basically nothing. Right? Now, we were talking about there being 3 kinds of programming languages here. Machine language, a low-level language like assembly, like we just looked at, and then a high-level language, which has a one-to-many relationship with the CPU. We like those guys. Okay, because, for instance, we're going to be using Python in here. We want to be able to just say print Hello world. Run. One line. Perfect. That's our kind of language. Then it turns into all that extra crap behind the hood, or under the hood, I guess. Let me just start the next slide so I can draw a picture here. So we have our high-level language, maybe like Python. And ultimately, that guy needs to run on the CPU. Now, you mentioned earlier that at the end of the day, it needs to become zeros and ones, right? Because that's what this dude eats. He eats zeros and ones. So no matter what happens leading up to this, we need to have zeros and ones here. Is that an O? I think I did an O. All right, zeros and ones. We need that guy before we can get to this guy. So we'll take a little break. When we come back, we're going to figure out how do we get from here to there. All right. So let's take 10 minutes. 10 minutes. That takes you to 7:30. So back here at 7:30. Butts in seat at 7:30.